So today we're going to continue our discussion on spinodal decomposition. I hope that I can go through all the topics on spinodal decomposition today, and probably start discussion on the Martin-Size transformation, which is a completely different type of diffusionless transformation that we never seen before. So that will be the Martin-Size transformation will be the last topic, new topic that we want to discuss. And we should be able to finish this on next Tuesday, fairly early. So, and then for the rest of the lecture on next Tuesday, I'd like to probably go through homework 5 problems in class. That's the plan for this today and next Tuesday. And on next Thursday, similar to what we did for the midterm exam, I'll prepare a review lecture that goes through the topics that we basically studied after the midterm. And in the final exam, we'll only, the final exam will only cover topics which we discussed after the midterm exam. So we wouldn't have any, I would say, a dedicated question to the concepts discussed before. But however, before the midterm exam, we talk about thermodynamics and kinetics, diffusion, these type of things, which are kind of a general tool that we're using all the time for the topics that we discuss after the midterm. So it's not exactly true that we're not going to touch those because it's not possible. Whenever we analyze a transition, we have to understand the thermodynamic driving forces, the barrier, and the kinetics, which is mainly diffusion. So, but we will not have dedicated problem, to these topics before the midterm exam, but we're certainly going to use the concepts and skills we learn. Okay, so that's the plan. So that in terms of the topics, we'll mainly focus on those we discussed after the midterm exam, which are mainly on the transitions themselves. Okay, so that's the plan for this week and next week. I think that's pretty much all we have, 3 lectures. And then I will try my best to post a study guide probably by the end of this week, and in which also I'll discuss some details about logistics for the final exam, which again will have separate sections, separate arrangement for the in-person quotation mark students and online students. So for the in-person students, I'm going to simply use the time that assigned to us, which is on the, I think, the Tuesday of the final exam week. Okay, so that will be the 27th, okay, in the morning of 27th. We have 2-hour window on this one. Yeah, we'll just follow the same format. I'll prepare a slightly different version of exam copies, right? And I'll send individual email to you for those. And for the online students, I will have a separate arrangement. I know most of you are working during the weekdays, so we'll probably find a time to do the exam over the weekend. Okay, so I'll provide more detail about that also. But you're probably going to see a different set of problems, but again, very similar to the ones that we use for the in-person class. So again, that's the plan. I'm getting some questions about final exam, and I will try to prepare the study guide with all the information that you need, hopefully by the end of
Can
the
I
week.
can I ask a quick question?
Yeah, sure.
Will you cover the whole syllabus, or it is after midterm one course?
What do you mean? So for the final exam, the major topics of the problems are focusing on the topics after the midterm. But because if I ask you to work on a problem of spinodal decomposition, you have to know some idea about the free energy, like regular
Yeah.
solutions, things like that, right? So I wouldn't test you against the concept of regular solution, but you may see, some related concept about regular solution in this spinodal decomposition problem. It's all the key topics we're gonna have in the final exam are after the first midterm exam, but there's no way we completely separate from the topics we discussed before because they're all related.
Yeah, I got it. Thank you so much.
No problem. Yeah. So yeah, so that's all I have for you now. Okay. So I hope it's clear. But again, let me know if you have any questions. I'm happy to address that. Uh, Also, the exam will be just like the midterm, is open to book and open to the lecture slides. Uh, so yeah, I think it should be straightforward. Okay, so let's start our discussion. Okay, so we have been talking about the Spinodal decomposition. I just want to quickly reveal what this is. Phenomenologically, what this looks like is that you initially start with a kind of homogeneous mixture of the solutes, right? And if you cool the system, and we know that just from the thermodynamic consideration, the free energy going to develop to local minimum. Okay, this means that if you're in the certain, so you start with a composition with right in the middle, for example, and this composition will not be thermally stable because we know by separating into two different phases with distinct composition, as basically suggested by the free energy curve, we can lower the free energy of the system, right? So this is what the system, will do, to lower the free energy by separating into two different phases. And this is basically the phenomena of spinodal decomposition. And we also discussed why you have curves like this, why the free energy wants to develop to local minimum as you lower the temperature. And one classic way or very useful model to understand this phenomena is through the model of regular solution, right? So you have a competition between the enthalpy of mixing and entropy of mixing, right? So the entropy of mixing always wants to, favors the mixing state because this will always increase entropy and which contribute a negative term to the free energy. So increasing entropy always reduce the free energy. And the higher the temperature is, the larger this contribution is, right? But on the other hand, if your enthalpy is competing against this effect, meaning that from the energy point of view, the atoms do not want to be mixed together because enthalpy is increasing if you mix them together. If this is the case, you set up a competition between mixing and demixing, which is dominant respectively by the entropy of mixing, enthalpy of mixing and entropy of mixing. So in this case, you see the key parameter to determine which factor going to win is the temperature, right? At a very low temperature, clearly I don't want to be mixed together because, in this case, I virtually have no contribution from the entropy. The only consideration or contribution going to be from the enthalpy. So I don't want mix because this increases the free energy. But on the other hand, if you have very high temperature, now the entropy term definitely dominant and you want to mix together. But from this very simple analysis, we know that as you increase or change the temperature, you're probably going to introduce a transition because you're changing the role of these two competing effects, right? So the high temperature, entropy wins, so system wants to be mixed together. But as you start to lower the temperature, eventually enthalpy going to dominate. And in this case, you favor demixing state. So this basically motivates or drives the spinodal decomposition to occur. That's the basic idea. And also from the free energy curve, suppose we have this symmetric free energy, right, which again is an example. We can easily use double tangent construction, which we've seen many times, to basically construct the phase diagram, right? So suppose this is your free energy curve at different temperature, and for each free energy curve at each temperature, what we can do is to do the double tangent construction, right? We find the equilibrium composition, okay, of the two phases, and then we map this composition on the corresponding diagram here. And we're going to construct, in this case, a solidus, which separates the mixing solid phase and demixing solid phase phases, right? So, and basically, if you connect the solidus together, you're going to have this coexistence. And this basically phase diagram. And within this phase diagram, we know that, okay, if your composition, thermodynamically speaking, in the equilibrium case, if your composition is within this dome, okay, you're favor the two-phase coexistence scenario, right? If you're out of this dome, you're okay, you can exist as a mixture, okay? So that's basically what we already know from the discussion of regular solution and from the thermodynamic point of view. Okay, so this is kind of a review, a recap of the regular solution and its thermodynamics. So now what we're interested in is because we already discussed a lot of transformations and we know, the driving force and barrier and kinetics, all of these interesting things. So now we want to kind of revisit this spinodal decomposition problem and using the procedure that we use to analyze all the other transformations to try to understand a little bit better, right? What exactly going on here. Now we know this is a phase diagram, but can we do better? Can we understand the transformation a little bit better about the driving force, about the kinetics, etc.? So this is what we are started to do starting from the last lecture. Okay, today we're going to continue. I think in the last lecture, what we did is to examine two different, um, composition, right? So we know that okay, any composition within these two x1, x2, favors a phase separate state in the thermodynamic limit, right? But in reality, can we really actually see these transformations occur? What is the driving force? What is the barrier? How these things play together to actually induce the transformation? Okay, these are the questions that we try to address. Okay, and in the last lecture, I think basically we examined two compositions. The first one is this G naught, okay, which is kind of already highlighted here, and the other one is right here. Okay, so you can choose a composition. I think it's probably here. Okay, so we have two examples of composition, and we know from the thermodynamic point of view, both of these composition favors a phase separated state, right? Because this is within this dome, okay, of the phase diagram. But I think we also already reached to the conclusion that these two, in reality, one of them can actually give us a spinodal decomposition, and the other gonna stuck in a mixing state, right? So basically, in this case, we can say we have good composition and bad composition. Okay, so now again, just to quickly recap what we discussed in the last lecture. So, and we call this G naught or X naught. This is going to be my good composition, right? Why is that? Well, because consider what is happening during the spinodal decomposition. Initially, what you have is just a homogeneous mixture, of the A and B atoms with average composition of X naught. But as we already, I think it's very familiar to us, the concept that we're always going to have fluctuations, right? Because of the atoms always moving around. So maybe at some point, okay, you have a fluctuation such that in one region of the system, you have a slightly lower composition, and in the other region, you have a higher composition, okay? So you have X naught minus and X naught plus, indicating that you have a fluctuation that leads you to have this locally separated two regions with different composition. Now we're interested in that, okay, how this fluctuation compared to this initial mixing state in terms of the free energy. Okay, so because that's basically what we gonna use to determine the stability, right? So which one gonna have a higher free energy? Is the original mixing state or this, phase separate state with slightly different compositions? Okay, based on the phase diagram, which one gonna give us lower free energy? Okay, we already showed in the last lecture, this one gonna have a lower free energy, right? If we choose our compositions to be X naught. Why this is the case? Well, if you follow this free energy curve, right? So initially free energy is right here, right, this dot. But then if you separate into two different compositions, okay, the lower composition gonna have a free energy right here, and the higher composition region gonna have a free energy here. And we know from the construction that we already discussed many times, if you just take this system and this system and literally glue them together to form a overall system in the phase separate state, the free energy of the whole system will be a linear combination of the free energy of each of the pure system, right? So it's basically linear combination. You construct a linear line, a straight line connecting these two free energy, and this intersection gives you the free energy for this phase separate state. Okay, now you can clearly see if our composition is this good composition, right, which is X naught, and by separating into these two different compositions, we'll lower the free energy by this very small amount, which is roughly here. Can we see this? Okay, I think this is clear, right? Okay, so this means, okay, it sounds good because initial composition, initial fluctuations leads to this decomposition, and it gives you a slightly lower free energy. Now, how about if we further increase the contrast? Okay, suppose that I flow more atom to the right region and flow more and take more atom from left region. So I increase the contrast between X naught minus and X naught plus. What are we going to see in those cases? Well, what we're going to see is that, okay, as these composition further separate, okay, and they move far away from one another, your overall free energies keep on decreasing, right? As the system keeps on developing this separation of composition, okay, and you reach the minimum free energy until, okay, your system reached the equilibrium composition predicted by the phase diagram, which is the lowest that free energy that you can ever achieve, right? So if you further move forward, you're gonna have an increase again. So Well, this means that, okay, everything are consistent, right? So if I'm in this dome that I know that the system wants to be in the two-phase coexistence regime, and if I start the transformation processes by having small fluctuations of x minus and x plus, I see that I have an immediate decrease of the free energy. Okay, and this free energy decrease or reduction is increasing, is enhanced as the separation keeps on going, separation proceeds. So this indicates that, okay, in this particular case, spinodal decomposition is going to happen spontaneously. There's no, at least based on our current analysis, right? We'll see later that there will be an effect of the interface. But in our current analysis, this means that, if you have a very tiny fluctuation, okay, to deviate from a homogeneous state to a slightly separate state, and this fluctuation will be picked up by the thermodynamics. You're going to use this to further reduce energy and enhance the fluctuation and keep on doing this. So you have a spontaneous, kind of phase separation, okay, in this scenario. Okay, so we just examine one particular composition, which is X now. Okay, I hope this is clear. Okay, well, how about this one? Okay, so let me erase, let me just clear all, I guess this should be okay. And redo that 2 lines. Okay, so, and we just examined the so-called good composition, right? How about now we do this bad composition? So I keep the good composition here. Okay, so how about we do the bad composition? Why I call this bad composition? Well, it seems that this one is also within the phase diagram prediction of the two composition within the phase diagram, for which we know the separated phase will be more stable and favored by equilibrium thermodynamics. But can this occur in reality? Okay, so what do we need to do to make this occur in reality? Now, if we do the similar analysis, say we start from a, kind of a mixing state. Let me change notion. Okay, so if we start from a mixing state, this is X naught, right? And then you have this two separate state, okay, with a slightly higher, a slightly lower, a higher composition. Okay, so initially I'm right here. Okay, now I follow the same consideration. So suppose I have a fluctuation to reduce the composition a little bit and to increase the composition a little bit, right? So and now I use the same analysis, see, okay, how does spontaneous fluctuation change the free energy? Does this lead to increase or decrease? And following the same analysis, we can immediately see that, okay, if you're separate or the fluctuation leads to the slightly different composition, you immediately increase the free energy. Okay, so this is for small fluctuations. But how about if I further increase the composition difference? Will this help? Well, we will see that for a wide range of composition differences, you're keep on increasing free energy. Okay, you can only decrease free energy until one of the composition for this one, gonna go far to this end. Okay, only in this case you start to lower the free energy. But to do that, you have to go over a very huge barrier. Okay, from the thermodynamic point of view. So this barrier is not due to any interface. Okay, this barrier is due to the nature of the free energy curve. So it's intrinsic barriers, not like the interface barrier, which is due to the smallness of the nucleus. It's not. Even for this case, no matter how large your nucleus is, you have an intrinsic thermodynamic barrier. Okay, that do not favor the kinetics of the transformation. So that's why we call this bad composition. Okay. So I hope this point is clear. Okay. So basically, from this very simple analysis, we see that, okay, although we know we can construct that dome, which I showed from the previous slide, right? Something like this. Oops, why it's not working? Like this, right? And we know that any composition within this dome favors the two-phase coexistence as the more thermally equilibrium state, right? As the lower, which has overall lower free energy. However, kinetically, or if you look at this, the possibility that to achieve that process, we see that not all the composition within the dome going to have the equal capability to really achieve that particular state of two-phase coexistence, right? We have good composition, we have bad composition. Okay, so we see two examples, but mathematically, okay, how do you distinguish the good composition and bad composition? Okay, what is the mathematical condition that tells you that this X naught is good composition and this is bad composition? Okay, so if we think about what we analyzed, right? So what's the key point to determine the good composition? The key point is that, okay, if you start from a composition and then the composition separated into two different composition with, a minus and plus, the free energy after the small separation has to be lower than the original free energy. Okay, so this means that you have a curve like that. Okay, and this is your point. Okay, now if you have a small separation and then connect the straight line between that small separation, you want this straight line to below the original curve. Does this make sense to everyone? So this is a geometrical condition. But what do we call that mathematically? Okay, if we have curve like that, so we want the curve to basically go like that. Okay, so to basically, to curve down like this. What is the mathematical condition, okay, corresponding to this particular geometrical scenario? Okay, so the mathematical term for describe whether the curve is going in this direction or in this direction is the convexity, or usually non-convexity or convexity or concavity of the curve. Okay, that is sounds familiar. A curve is convex, I think, which means that it's going to bend. I think it's probably bend in this way. Okay, so if bend in this way, we say the curve is non-convex. Okay, so you see the convexity of the curve going to determine a good composition and a bad composition. And mathematically, what determines the convexity or non-convexity of the curve? Well, it's the second order derivative, okay, of that curve. It's going to give you this information. Why the second order derivative is doing that? Well, you can clearly see that, again, it's very geometrical, so should be very intuitive. So basically, if you see, okay, so if the curve is bending this way, right, and we can do, local derivative. Say I'm doing this slope of the curve, right? And if the curve is bending in this way, okay, bending like this, okay, so how do you think the derivative is going to change? If we take derivative of the curve at each point and see and follow this particular line, follow particular this path, and we keep track of how the derivative change, okay, what do you think the derivative is going to change? Is the derivative going to increase or decrease if the curve bend in this direction?
Decrease.
The derivative is decrease, right? But what is derivative? The derivative is basically, so your if the derivative is decreasing, this means what? So this means that the derivative of the derivative of this free energy curve, right? Is this going to be positive or negative? If the slope of this curve is decreasing, right? So this is the slope, dg dx is going to be the slope, right? And if the slope is decreasing, so this means that if we take the derivative of the derivative, that's going to be negative. Does this make sense? Because this thing is a monotonic decreasing, right? So if you take the derivative of this decreasing function, we're going to get a negative. Okay, so for the same reason, so if you look at if the curve going to bend in this direction, which corresponds to this part, okay, so if you do the local derivative, okay, what are you going to see? Is the derivative increasing or decreasing? The magnitude of this derivative?
For the convex, it would increase, and for the
It's increasing, right? So this means that for this part, right? For this part, the derivative of the derivative, which is the second order derivative of the free energy curve, is positive. Does this make sense to everyone? Okay, so see that we can use the second order derivative to distinguish the convexity or concavity of the curve. Okay, and then, if we look at this particular curve, you start with this convex branch, right? And then eventually you go into your transition to concave branch or non-convex branch. So this means that there will be a critical point on the curve that marks the transition from the convex case to the non-convex case. And also we consider that this curve is continuous. So the second order derivative should change continuously from positive to negative. So there has to be a point which marks the transition, which corresponds to the second order derivative of the free energy curve with respect to composition equals to 0. Does this make sense to everyone? Okay, so these 2 points, which corresponds to the second order derivative of the free energy curve with respect to composition equals to 0, these 2 points marks the separation between good composition and bad composition. Okay, because for any composition within this concave regime or concave branch of the free energy, if you do that analysis, you always see, okay, a spontaneous fluctuation will always decrease the free energy, which is going to lead to the spontaneous spinodal decomposition. And on the other hand, any composition in this convex regime or convex branch, if you have a spontaneous fluctuation, this is going to increase the free energy, and you will never see the spinodal decomposition can occur. Okay, does this make sense to everyone? Okay, so this means that, okay, if you look at the curve, now we have something more interesting to look at, right? Because from previous analysis, we know that the only thing we should look at is x1, x2, which can be obtained by double tangent construction. And once we know these two, we know the boundary for the phase diagram, and we can construct that. But in this particular example of spinodal decomposition, we see that there will be an inner envelope, right? So this will be my outer envelope for the thermodynamically, coexistence region. But there will be an inner envelope, which is defined by these 2 points. If you just do a kind of extension for the line on this one. Okay, so I'll call this x1 star and x2 star. Okay, so these 2 points actually marks the distinction between good composition and bad composition. And we know that any composition within this smaller envelope going to have a spontaneous separation, right, that occur in the system. Okay, so this means that, okay, if you have 2 A and B atoms, you try to mix them together and prepare a composition within this inner envelope regime, they will never mix. Okay, so we call this the miscibility gap. Okay, so but that basically what I want to tell you. I think this is very physically intuitive, and even the mathematical condition seems to be a little bit sophisticated, but it's all based on the geometry and our understanding of this condition for thermal equilibrium again. Okay, based on free energy. Okay, I hope this is clear. Okay, so I'm going to move forward. So basically, we know that now for each temperature, besides looking for this x1, x2, we can always also need to look for x1 star, x2 star corresponding to this condition, right? Which defines the miscibility gap. Okay, so now if we do that, do we have, yes, I think this is like a little bit more rigorous mathematical analysis. Okay, why that, from this basically, which I just erased, the analysis basically is from very simple geometrical consideration, but we can derive exactly the same condition from a little bit more physical analysis. So the basic idea is did exactly what we did graphically. Okay, so basically what we need to do is to look at the free energy difference. If I choose this composition, right? So I need to get a delta G free energy difference. But now suppose this is just a symmetric decomposition. So I do not, in this particular case, I do not, choose a weird composition. So I have a different combination parameter. For now, I just choose, or at least when this delta X is very small. So delta X is the, the separation or fluctuation that give you an increase of X compared to X now, or decrease compared to X now, right? So this is going to be my X now plus, and this is going to be my X now minus. So, and now I just write down the free energy for the phase separate case, right? And what I do now is I do Taylor expansion for this term and for this term, okay? So, so if I do the Taylor expansion for the first term, I keep the first, this is a constant term, this is the first order derivative, this is second order derivative. You can keep to higher order, which is this one. And then if you do Taylor expansion of this guy, you're gonna get the same terms, but because this is a negative, okay, so basically I have a negative sign right here. And then this is the second order, okay? So this is my free energy after the transformation, and these 2 terms cancels one another. And what you have is you can end up with a G naught, right? Which is this Gx naught. I call it G naught because they have factor of 2 and they have 1/2. So this is just the G naught. And then you have this 1/2, okay? And this is the second order derivative, which is right here, and then this delta x squared, right? This is the free energy after you have the phase state, but with very small fluctuations. And then the free energy difference is that take this term, the free energy after the separation, minus the original free energy, so that this G naught term is gone, and the only thing left behind is going to be this term. Okay, this is going to be the free energy difference before and after. Okay, before and after the fluctuation, right? It's clearly proportional to delta x, which is kind of the driving force, but also the key factor, because this is going to always be positive. So whether the free energy difference is going to be positive or negative can only depend on which factor. The second order, let me do this again, the second order derivative, okay, of the free energy with respect to composition, which is exactly this guy, right? And mathematically now you can see when this guy is negative, which means that we're in this concave part, we have a reduction of free energy. So go ahead, do the transformation. And when this part is, and when the original composition is in this convex branch, this part is going to be positive. So you're doomed. You cannot do that transformation because it's going to give you a such increase of the free energy. Basically, again, using the rigorous thermodynamic considerations, we reach exactly the same conclusion from our geometrical illustration. So that basically showing you again. Okay, so I get a question, but I will explain that later. Okay, so this again is we redid this same processes and getting the same condition. Okay, so yes, so this is a condition for the Spinodal decomposition. Okay, so now this is some kinetics. Okay, let me show this. Okay, so I have a question about the miscibility gap. Okay, as defined. So this is a very good question. Okay, so typically, let me see. I think I have a explanation for that. Okay, so how do we define the miscibility gap? Okay, so typically the miscibility gap is defined as the outer dome. Okay, that's just from my understanding, but I think there might be a different way to doing this. But miscibility gap is defined as the outer dome. Okay, and then the inner dome or the inner envelope is typically what we call the chemical spinodal, which means that if you're within the inner dome, you have spontaneous instability. So you're never going to have any metastable state. If you prepare the system within this inner dome, there's no way that you can ever stay as the mixing state, when you lower the temperature. Okay, but if you're in the, for example, outer the inner dome, okay, there's still a possibility that you're, get stuck in this mixing state, although you want to be demixed. Okay, so that's I think at least from the textbook that we're using, I think this is the notion that they define these type of things. Okay, but again, I'm not 100% sure that if this is a way how all field is using. Okay, but typically we just use the outer dome to define the miscibility gap, and the inner one is called the chemical spinodal, in which that you have instantaneous instability. So that's I think what we agreed on. Okay, but anyway, so but you feel free to correct me. Okay, if you see people are using different notion in their own research. Okay, but anyway, so this is I think the driving force part I think is kind of clear for this one. And now we want to say a few things about the kinetics part, which is very interesting. The reason that is interesting is I think you can already see that if you simply look at what happens during the Spinodal decomposition, right? The normal idea of diffusion that does not seem to be working here, in the sense that you start with an initial homogeneous mixture, right? But in here, there's no structure change. Everything's the same structure. So you're just dealing with diffusion alone. So this is different from like eutectic transformation and things like that. But so you just deal with the same solid structure and only deal with diffusion of the solutes. But what you see, or motion of the solutes, I'll say, rearrangement of the solutes into different regions. But the thing that you see here is that, from the diffusion point of view, from, if we consider okay, this kinetics is diffusive, what you see should be, this is going to be our starting point, right? And we did this many times when we discuss diffusion. Okay, you're going to start with a flocculation like that, and diffusion will do what? The diffusion will smooth out the flocculation and take you from this case all the way to this homogeneous case, right? This is what we know about diffusion. It should go from from right to the left. But if you look at spinodal decomposition, okay, what should be the direction to see the evolution of solutes is completely different, right? In the spinodal decomposition, what you do is that you start with a homogeneous mixture. You build up some small fluctuations, and then these small fluctuations get enhanced and enhanced, and they're favored by the thermodynamics, and then eventually you end up with a very inhomogeneous state. You have the two phase separate state where you have nearby regions with very high and low composition, corresponding to the X1 and X2. I'm sorry, this is going to be X2, and this is going to be X1. Does this make sense, everyone? Okay, so this is phenomenologically what happens. So why this is interesting? Well, because you see a particular kinetic processes go against the diffusion. So the atoms move actually not downhill the gradient, but uphill the gradient. Okay, it's actually keep on aggregating to increase the gradient instead of decreasing. Okay, it's enhancing the flocculation instead of smoothing it out. So what happens here? So so basically, if in this case, clearly we know, the normal diffusion does not work. Okay, so but what is the key gradient in the typical diffusion that we discussed? If you still remember, when we start our diffusion, what is the physical model or the physical assumption that we start with? What the atoms are doing during diffusion that leads to the conclusion that you're going to have atoms on average move from the high concentration to the low concentration end. Do we still remember that? Let me see, do I have any? Yeah, this is the observation, but because it's handwritten, I don't think I can show this. So if you think about diffusion, you're going to have a negative diffusivity, right? So this is quite annoying. But if you think about, what is the mechanism we talk about diffusion? What is the key mechanism? When we construct these atomic planes, what we're assuming the atoms are doing there. Any thoughts?
They're moving from high concentration to low concentration.
Yeah, but that's the consequence, right? If you go back to the atomic model that we have the planes, we construct these planes, right? And we see, you have a little bit more atom on this plane, but have less atom on this plane. And overall, from our analysis, we see that this is going to be a flux in this direction. But what we're assuming that these atoms are doing, if you look at a single atom, is there any preference that this atom wants to go to the left or this atom to go on to the right? If you look at a single atom, is there any preference where the atom wants to go?
It will move if there's a vacancy.
Yes, there will be vacancy. Assuming that this is like a interstitial diffusion, so I have a lot of vacancy, a lot of room. In all directions, there are many room for the atoms to hop. Is there any preference for which direction the atom wants to go? If you're just looking at a single atom.
It depends on the structure.
Yeah, but assume that we have symmetry. See, we have cubic symmetry and all the directions have the same equivalency. In that case,
It's same in all the direction.
the same in the other directions, right? So in this case, the key thing that we assume that the atom has no preference. At each individual atom level, there's no preference where this atom wants to go, right? So it has equal probability to hop from left to the right or from the right to the left. The reason why you see there is a overall flux is simply because on this plane, you have more atoms, right? So on average, there will be more atoms hopping in this direction than there are atoms going back on this plane. So this random hopping of atom model leads to the conclusion that, okay, the flux is proportional to the concentration gradient because whenever on a plane you have more atom, these the random hopping consequence will be these atoms gonna eventually hop to a plane with less number of atoms and so on, right? So this is the key when we derive all of the Fick's laws for the normal diffusion. Why the fluctuation wants to be smoothed out? Because it's just doing random hoppings. Does that make sense? Okay, so by the doing random hoppings, what we mean is that it doesn't really matter where the atom is in the structure, it does not feel any difference in their chemical potential or their molar free energy, right? So they're just doing this random hops without any driving force considering their energy. Does this make sense to everyone? This is what we know about normal diffusion, okay? And it's very important assumption that atoms are moving around in a random fashion. But is this also the case in the Spinodal decomposition? Does the atom themselves don't know where they want to go and just do the random hopping, or they have a clear idea where they want to go? Because it can lower the free energy. It's the latter, right? I'm sorry, what you want to say something?
Oh, I was just gonna answer your question that they have a direction that they want to go.
Exactly, they have a direction they want to go because they want to lower the free energy, right? They know that, okay, if they move to that part of the system, like in this one, if the B atoms move into the region where you have a clustering of B atoms, it's going to lower the energy because the enthalpy going to be lowered, right? The free energy going to be lowered and the chemical potential going to be lowered. Okay, what is chemical potential? It's simply the molar free energy of the atoms in a mixture. That's the same thing as the free energy, right? But on atomic level. So again, we will not derive anything more detailed than this, but I think it's more important for us to really understand what's going on and how to rationale this apparently abnormal diffusive behavior is because in here, the atoms know where they want to go. Okay, for each individual atom, they want to lower their free energy. So the motion or the flux of the atom in this case is not driven by the concentration gradient. Okay, because in the case of random motion, they're driven by the concentration gradient. But in here, the motion of the atom or the flux of the atom is driven by lowering or the tendency to lower the chemical potential. So the flux in this case, if you want to write it down, okay, which I won't do the derivation for you. If you want to write it down, the flux is going to be proportional to, the chemical potential. I think there should also be a negative sign here. Okay, proportional to negative of the gradient of chemical potential. And you can actually have the same constant in front of this, but that constant is not called diffusivity, it's called mobility of the atom. Okay, but again, I won't go through more detail than this, but this is just a very interesting phenomenon to note and to revisit our understanding of diffusion and to see why here you have this apparently abnormal diffusive behavior, because now the driving force is not concentration gradient anymore, is the chemical potential gradient. Okay, so that's that part. And let me see. So that's for the kinetics part. And then, okay, so this is for this, overall, if we consider the, spontaneous, the chemical spinodal and consider that. So we have a slightly revised phase diagram, highlight those regions for the very strong miscibility gap defined by the chemical spinodal, which we have already touched on. So here I want to, so basically up to this point, we have talked about the driving force, which is the bulk free energy reduction if you're in a good composition regime, right? But we haven't talked about the barrier. Okay, and probably, let me see, yes, I already showed this for you. So basically you can see in this case, we also have a barrier, but this barrier is kind of interesting because the barrier itself is not very important in the beginning of the processes, but gets stronger and stronger at the end. Now, what do I mean by this? Well, if you think about a normal nucleation processes, right? So I'm just going to remind you. So if you think about normal nucleation processes, right? You start from a homogeneous liquid, for example, and then you create, suddenly the flocculation is going to create a solid. So this is a kind of a very sudden processes, right? You just have fluctuations and the atoms within the small solid region, they get this crystal structure and you create a small solid. And accompany with, in the same time that you're creating the small solid, you also create an interface, which is very sharp. in the sense that you can clearly distinguish liquid and solid structure. Does that make sense, everyone? Right? I think this is okay. And for the same reason that for the Spinodal decomposition, you have similar of these alternating stripes, but most of the cases these stripes in the Spinodal decomposition, I'm sorry, in the eutectic transformation, they have distinct crystal structures of alpha and beta phases, right? So although you still have to worry about the difference of the composition, but the crystal structure already give you a huge increase of the mismatch strain energy that's going to cost you a lot for the interface. So those are the typical understanding of the driving force and the barrier, especially the barrier due to the interface. So now the question for us for the Spinodal decomposition is that, do you have interface in this case? And if so, how do we probably take into account this increase of energy or energy barrier due to the interface? Okay, so that's the question, which is kind of interesting. Okay, and it's quite different from all we know. Okay, so the first question that, is there an interface in the system?
Yes.
Yes, right? Clearly after the separation completes, we have an interface because you have this huge distinction of composition, right? So in those cases, the two phase are well defined, you have an interface. But how about in the beginning? If we just start the separation, like we analyze the initial separation, you have, this X naught here, okay, and you have, slightly separated composition with X naught minus and X naught plus, and in those cases, I mentioned, the interface is not quite important, okay. So why in that case the interface is not quite important? If we just, look at a very, very small separation.
I mean, because they're very close to each other, right?
Exactly. They're because very close to each other in terms of composition. So the atoms, they virtually not feel a thing if you move from this part to this part. Okay. So you see, this is kind of interesting. So the interface in this system, okay, which is basically depend on, if you go from one direction to the other direction, how sharp of the difference the atom feel, right? In all these cases, if you travel from one direction to the other, the atoms feels a very sharp change from one phase to another. But in this case, in the Spinodal decomposition, the phases are gradually developing. So the atoms initially do not feel a very sharp change in their environment. So they do not feel an interface. And this interface is gradually developed during the transformation. Do we see that? So this, typically what we call in this case that we have a diffusive interface, okay? In contrast to the sharp interface in these two cases. Of course, you can argue that they're on atomic level, these interfaces are still kind of a little bit smooth and not very sharp, but in our analysis, compared to this case, these interfaces are sharp and this is diffusive. Okay, so that's the concept. Okay, now the question is that, in this case, if the interface is gradually, developing, and it's kind of diffusive, not very sharp, how can you mathematically count this interface into account for the energy barrier? Okay, well, the thing that we do here is that, how do you define interface, right? If we say the interface is from, it's can sudden change the atom fields, is, basically we can consider that it will, related to some gradient of the concentration gradient, right? If you go from one phase and one region to the other region, right? So you have some gradient which associated with the drop of composition, which is delta X, right? And also is associated with the distance over which this composition is going to drop. Okay, so that is basically how we define the composition. Okay, it's quite clear to see at the end, but even in this case, you see, we can define it, and lambda is basically a wavelength between this peak and this peak, right? But you can basically consider lambda going to carry or characterize this distance over which your composition going to drop from the peak to the valley, right? It's a 1/2 of lambda, but basically it's on the same scale of lambda, right? And the drop of the composition we define to be delta X. You see, so basically if we use delta X over lambda, this basically tells you or provide a rough estimate of the sharpness of the interface, right? Or how fast these things going to change over a small distance. Okay, and initially we see this going to be very small, right? Because your initial lambda you can consider is not going to change a lot, but the initial difference in the composition is very low. Okay, you start from all the beginning and then this things keep on increasing. So based on this, and there's some very nice argument which will not show. We just use this intuitive picture to explain this, but there's a deeper mathematical derivation which we will not discuss. So we can consider that the energy barrier, which is due to the interface, is simply proportional, right, to this thing, okay, to this difference of the this gradient of the composition as you travel from one phase region to another. Okay, and there are higher order terms you can add to this, but this is the first order term. Okay, so and if you combine these two together, okay, now we know how to deal with the driving force, and now we know how interface play a role during the entire processes of the separation. So now we can combine these two together. Okay, so let me clear this. So, and we can combine these two together. Yeah, also there's a strain energy, I'm sorry, to the system, although they have probably the same crystal structure, but because the atoms are of different sizes, so there might be a strain energy related to this, okay? Basically, again, I think this is okay. The strain energy is proportional to delta X, okay, which is a composition difference, and K is the bulk modulus, Vm is the molar volume for the system, and eta I think is a strain. Okay, so this is basically, so suppose the lattice here is A, and this is change a little bit. So if you go through this region to this region, you have a change of the lattice. But we're writing down the change of the lattice parameter as a function of composition. Okay, so if your composition varies a little bit from this region to that region, you have a slightly change of the lattice parameter, and you get a strain here. Okay, so basically for the same consideration, we write down the strain energy as a quadratic form. Okay, this is kind of a spring constant, and this is very much like the displacement of the strain, right, or of the spring. So you have this relation. Okay, and altogether you have another contribution for the strain energy for the system. So this is another source of barrier that you build into this because it's a solid phase transformation. Okay, so putting all of this together, so we have the driving force, which is delta GC. Okay, and we have the contribution from the interface, I think which is this one, delta G gamma, which already derived as this guy. Okay, and then we have the barrier from the possible strain energy, which is given by this guy. But we were able to formulate all of these energy terms and barriers in the form of the delta X, which is the initial fluctuation or the difference of the composition, deviation of the composition from your initial composition. Okay, so consider all of these two terms together. We have the overall free energy difference. Okay, the overall free energy difference for all composition, okay, is going to given by this. Okay, so now again, in the first set of analysis, only focus on this one because when delta X is very small, these two terms, the contribution of these two terms are very small. Okay, so if we want to see whether the transformation can start or not, but looking at the thermodynamics, we do not have to take into account these two terms. But as the transformation proceed, right, as the contrast of the composition are getting larger and larger in the two regions, now eventually the interface begin to play a role, and the mismatch lattice also play a role. And the interface is going to have so if you compare the terms, okay, this one going to be larger than this one, and this one going to be larger than this one. Okay, so because they roughly have the same crystal structure, but just a slightly different spacing of lattices. So this elastic energy contributes, least to the energy, and then the interfacial energy contribute next to that. But this one may play an important role towards the end. Okay, but the major contribution from the bulk free energy consideration. So that's basically for this one, so this is the change of free energy for all composition. Okay, starting from the beginning, you only have the first term, and as the system start to change to separate more and more, you actually start to have contributions from the second interface term and even the volume bulk mismatch term. But this equation holds for all composition difference. Okay, so now after that, okay, so if we have this, we can write down the condition for this spinodal to occur. Okay, so now if you want the spinodal combination to occur spontaneously and continuously, okay, you don't want to, you know, initially happily start the separation, but you don't want to get stuck at some stage when the interface begins to play a more important role, or eventually the bulk gonna dominate, right? If you don't want that to occur, so you want to guarantee that, okay, the bulk free energy reduction term, which is given by this one, gonna, you know, be larger or overwhelm the other two barrier terms for the entire range of separation. Okay, so that is the condition you have. Again, you just need to have a large enough driving force associated with bulk free energy reduction compared to all of the two surface terms. And in most cases, I think we're just to compare the first two. You know, for most cases, we do not quite take consider this one because it's very small compared to these two terms. Okay, and I don't know whether I have a slide for you or not. Let me check. So for certain lectures, I think in certain different classes, you know, this is the key ingredients to construct the so-called phase field model. Okay, for these systems, you can, when you write down the phase field equation, basically you have to construct a free energy functional as a function of the, you know, this field, right? This phase field, which is the phase parameter, which is this delta x. And for those cases, you need to worry about the development of interface, and we're using very similar considerations and these ingredients to build into our phase field equations to simulate evolution processes, which that, you know, the simulation that I show, let me quickly go back before this one. Okay, so this is a simulation that generated from phase field models. Okay, it started with the free energy and also built into the effect of interface and also the bulk free energy. I'm sorry, the mismatch of the lattices. But you can see the reason why initially you start with the separation, but why, you know, all of these things goes to circle shape, and why the bulk blue and red phase get coarse and coarsen. Why do you think the system is doing that? Once it separates, you know, it basically indicates that, okay, to satisfy the free energy requirement, but why, you know, the system all become like circle eventually, or why the interface are optimizing? What is the benefits of having circular shape?
Reduced area.
Reduce the area per unit volume, right? So the reason why that you see, you know, initially why it's not important, because initially the interface is not quite important, right? Because we have diffusive interface, but the end of the separation, you have sharp interface. So we want to minimize that. In this case, there's no way to reduce the energy, right? Because I already have the separation occur. So what I can do is that I can reduce the interface area, right? I can optimize the shape so that it can become circular, and this will lower the area of the interface, which clearly indicates the role that interface play towards the end. Okay, does this make sense, everyone? I think this is all I want to tell you about spinodal decomposition. Okay, so again, yeah, this is just a quick recap of the topics. We introduce the concept, we revisit the regular solution model, which is beautiful for studying spinodal decomposition. And we'll talk about the driving force and barrier. And in the kinetic part, we show that this is a very excellent example that you have abnormal diffusion. And in this case, the flux of atoms are driven completely by the chemical potential gradient and has nothing to do with the concentration gradient. Okay, so that's all I want to say about spinodal decomposition. Any questions before I switch gear and talk about, let me see, the last topic. Okay, so if there's no question, let me move on. Okay, so this will be the last new transformation that we're going to discuss in the class. Okay, I know we'll talk about so many different transformations, but I guarantee this is going to be the last one. Okay, so so this is called Martin-Side transformation. Okay, or some people wants to call this diffusionless transformation, and we'll see why that's the case. Okay, so if you don't have any question about spinodal decomposition, let's start discussion. Okay, so yeah, this is a kind of a list of topics. We're going to introduce the concept of diffusionless transformation. Okay, so if we have diffusionless transformation, this means we have diffusional transformation. Okay, and if you think about it, all of the transformation that we have been talking about are diffusional transformations, because it all involves kinetics that, related to the motion of atoms from one phase to the other, right? Whether it's diffusion is driven by chemical potential or driven by the concentration gradient, but they're all involve diffusion of atoms. But in here, we have a system, we have a transformation which involves no diffusion at all. Okay, and as you can probably imagine, how can you prevent diffusion to occur? You have to make the transformation very fast, and you have to cool the system so that the diffusivity of individual atoms is very, very small, right? So, and then we basically can probably imagine that these transformations typically occur for faster cooling, and that is exactly what happened. And in this case, we also need to, since it's a transformation, this means nature won't do anything that is not beneficial. There's no free lunch, right? Since there is a transformation, there has to be a way for nature to use this to reduce the energy. So there will be a driving force, and we'll see if you're not achieving the transformation through diffusion, what is the pathway that you're gonna, realize this transformation, right? And finally, we're gonna consider the geometrical consideration of the barrier, because in this case, there's no diffusion, right? So the barrier and the driving force are kind of different than what we have already considered before. So that's basically kind of an overview of what we can discuss. It's quite interesting. It's completely different than what we already know. So it's refreshing. Again, so now basically, to introduce this diffusionless transformation, we just look at what we already know about the diffusional transformation. Again, I'm looking at this, precipitate growth and enucleation growth processes, which we just looked at a couple lectures before. So if we start from alpha phase field and then start to cool the system, physically what happens is that because we lower the temperature, we lower the solubility of of B atoms in the alpha phase. So these extra B atoms are going to come out like sugar, come out in a super saturated water solution. So to form a different solid phase, what we call precipitates of beta. And we know that this process is diffusion controlled, right? And how fast this beta precipitate can grow in both thickening and lengthening modes depend on the diffusion. Okay, so this is a normal diffusive transformation pathway. However, as you can probably imagine, okay, now if I do not do this very slow cooling, so I give the atoms a sufficient time to diffuse around and to grow, into the beta phase, I do this very quickly. So typically we call this quenching, okay, which means a very quick drop of temperature to the system. And do the quenching. What do you think gonna occur in those cases? If we do not give the atom sufficient time to diffuse around, okay, what do you think gonna happen?
The crystal structure that's present at whatever temperature you had will freeze.
Okay, so basically whatever, the B atoms are randomly distributed in the A atoms of the solution, right? But if you do not give them sufficient time to diffuse around to form a second phase, what happens is you just freeze everything in the original position, right? So this is very intuitive. And indeed, this is, most of the cases what you're gonna see, okay? So, these atoms gonna, most of the cases, the solutes gonna freeze in where they are in the system. Now, however, okay, they're very, very unhappy about this, right? Because, they're getting stuck in this high energy state where they can't have a lower energy. So they're very unhappy about that. But there's nothing they can do through diffusion because you already cool the system at a very low temperature. The atom is not moving around at that low temperature. But, nature is very smart, okay? They actually impose another, invents or adapt, I would say, another pathway to lower the free energy, not to the best that they can, but still lower the free energy, okay, a little bit through a spontaneous, I would not say spontaneous, a global, fast transformation involves the change of the entire crystal structure. Okay, so this is Martin-side transformation. And the consequence of that is that you wouldn't see, these precipitates, which are these dark regions. You're going to see these guys. Okay, now these are not precipitates. These are, you can clearly see there are things within within the bulk, right? In this case, the green boundaries are very clean. You don't see any precipitates, but you do see these things. These are what we call the twin boundaries or shear bands. Okay, they're the indication that you have accumulated a huge amount of strain in the grains. So these strains are localized and released in certain narrow regions. Okay, that's the consequence of that. But why you accumulate all these strains? What happens in the system? Okay, and this is what we're gonna discuss. But basically, this is kind of the concept, right? So we'll fast cool the system. Okay, we call quenching, and everything gets stuck. There's no way for it to diffuse around, and the system is very unhappy. But there's no way for the system to lower the free energy using the normal pathway involving diffusion, involving the motion of atoms. So they will adapt to a different pathway, which also allows the system to lower the free energy a little bit. Okay, but through a global transformation. So that is the Martin-side transformation that we're going to discuss. Okay. So is this up to this point? Is that clear? So I understand this is a little bit, probably confusing at this stage, but we'll see an example. I think that will be immediately clear. Okay, so basically the Martin-side transformation involves no compositional change. It's a sudden global rearrangement of all the atoms and change crystal structure. Now, again, this is a sketch of the transformation pathway as a function of the cooling rate. Okay, so if you cool very slowly, you're going to have nucleation growth. You may not get the best results for that, but it's very tolerable. But if you cool super fast, okay, this is a 50, but this is like 50,000 Kelvin per second. Okay, if you drop the temperature very quickly, you're able to produce the Martin-side transformation. Okay, now the massive transformation is kind of means that you don't have a global Martin-side, but locally you have this, mechanism happening. Okay, so this basically means that we have very fast cooling rate. Now, what is the driving force for the Martin-side? Okay, so let's look at this phase diagram. So now suppose I start with, how much time do I have? Okay, so I think this is probably the last I can mention. So suppose that we have this X naught, right? And we know that we start with alpha phase field, which is here. But now if I cool the system to, this is already the cooling. So in this case, at a particular temperature, you have this two free energy. And we know that if the system is in equilibrium, I should actually have the two phase coexistence. Okay, so, the system is going to separate into this alpha and beta composition. Okay, and my free energy going to be like here, right? So I can reduce the free energy by this whole amount, which is the free energy or the driving force for the equilibrium transformation, where I involve the nucleation and growth of the beta phase. Okay, but if this is not possible, okay, if the system is completely stuck in the alpha phase, okay, the free energy will be as high as this. Okay, so this is the highest free energy that you can ever imagine at this composition, right? So you have three choices. You can stay as alpha, and the other choice is that you can have the separation, which is the best, but you cannot have. But don't forget that there's a intermediate choice, which is this. Okay, so what does this mean? Well, this means that, okay, I cannot completely transform into beta, alpha plus beta phase, which give us the best combination and best results in terms of the free energy reduction. But I can always, lower my free energy in this particular case by switching from the alpha branch to the beta branch, right? So I start with alpha, but in this case, I can switch from alpha to the beta. Okay. Now, here's the key question for you. Now, if we have that, if you compare the difference between this state where I highlighted using the blue circle and this state, which I highlight with a yellow circle, okay, what is the difference between these two phases? Now, normally when we contrast the difference, we'll compare their number one, crystal structure or microstructure, and number two, the composition. Now, in this case, if I ask you to compare the difference between these two phases, what are the difference they have?
Crystal structure.
They have different crystal structure. Do they have any difference in terms of composition?
No.
No, right? So this means, this kind of give us an interesting hint. Well, this means that, okay, everything gets stuck, right? Because you freeze the system to a very low temperature, so the atom is not moving. This is fine, right? I don't have to change composition. I can have my alpha phase and the beta phase have the same composition. All I need is a change of crystal structure. If I can actually have the change of crystal structure with the same composition from the alpha branch to the beta branch, this also allow me to decrease the free energy a lot, right? Not to the best I can, but still can give at least a reduction of free energy by this delta Gm, which M indicates the Martin-side transformation. Does this make sense to everyone? So this is the driving force for the Martin-side transformation. It's a non-equilibrium transformation. It occurs under the constraint that there's no diffusion, so your composition cannot change. But nonetheless, if there is a method or a pathway for me to immediately jump from the alpha branch with a different crystal structure to a beta branch with another different crystal structure, I can still reduce my free energy. Does that make sense to everyone? Okay, so you see this is already we see a possible way to reduce the free energy without changing the composition, right? If you do not allow me to change the composition, it's fine. I can change my crystal structure. Okay, is that clear? Because I think this is a very important distinction from all the other transformations we discussed. Okay, so now if that's the case, we have to see, well, okay, this sounds a reasonable plan, but can you actually do that? Okay, if if there's no pathway for you to freeze the composition, but just to change the structure, you can also not, there's no way for you to achieve this, right? So you have to show me, well, it's a promising driving force, but kinetically there has to be a pathway to realize this. Is there a pathway to realize this? The answer is yes, of course, because we already know this occurs. But I don't think I have time to finish this. But I will start. Okay, this is quite interesting. Okay, now suppose, and this is where I know that I get a lot of questions, so I'll try my best to do that. Okay, suppose that my alpha phase has a FCC structure. Okay, and my beta phase has a BCC structure. Is quite reasonable because they're all cubic structure, but they're different. Okay, so apparently is if you just work with one unit cell. And by the way, this is a FCC unit cell. Can we see that? I only show the atoms on the center of the faces that we can see here. Okay, and then there are atom on the face center here, here, and here. Okay, I hope this is clear to everyone. So this is FCC unit cell, but I take two of the cubes and I show them side by side. Okay, is this clear to everyone? Okay, just want to make sure. And this is clearly a BCC unit cell. Okay, so now if you just look at a single FCC unit cell and a single BCC unit cell, you may say, okay, they're all cubic, but besides that, there might not be quite, a clear way to connect them together. But the answer is no, right? If you look at these are structures that are repeating themselves throughout the space. So if you just look at one unit cell, you may not see a connection. But if you look at the way that how I show this, you look at two FCC unit cell side by side, right? And in here, okay, and focus on my guide. Basically, if you take these two atoms, okay, and then you take these two atoms on the surfaces, right? And you do the same thing at the bottom. If you take these two atoms, define the edge of the cube, and the two atoms at the center of the surface, okay? And if you can, you consider that these two rectangular face, okay, I think it's probably square face. These two square face, okay, defines a cuboid, okay, that you can actually kind of segment out from the FCC structure. You see that this segment has a structure which is at least have some similarity to the BCC structure, right? It has a stretched box, but it has squared face on the top and square face on the bottom, and have rectangular face on the side, but it has one atom right in the middle of that thing. Can we see this? Okay, this is basically, it's a different way, right? You can tessellate the whole three-dimensional space using the FCC unit cell, but there is equivalent manner for you to tessellate the entire space into these guys, even you have a FCC structure. Okay, so, and this is going to be our initial step for understanding the transformation pathway. And for the sake of time, I will stop here. Okay, I will continue our discussion on this one. We shall hopefully we'll find very, very interesting. Okay, so I'll
I
stop
have a
recording.
question.